This week we are talking about sets relations and operations, the concept of power set, Cartesian product, and the very important concept of relations. And in the context of relations, we are going to talk about the properties and closures of relations. And then based on the properties that a relation can have, we are going to talk about two important types of relations, equivalence and ordering relations. Let's start with sets. Um, I'm assuming probably all of you are familiar with the concept of a set, but let's go over the basics quite quickly. A set is an unordered collection of objects which are called the elements. Of course, we know the basics. The order of the elements do not matter and repetitions do not matter. You just have a collection of elements. And this is the notation we use for an element being in a set or not being in a set. And of course, we have the different ways to represent a set. Here we have the raster method or the list method. You have uh, 5 elements, for instance. In this way, you can just list the elements inside curly braces to indicate a set. Of course, as the number of elements increase, this method becomes cumbersome or maybe less useful. And to be more effective, we use what we call the set builder notation. Here we just define the set using the common property, let's say, if there exists such a property of the elements. For instance, this set here, we can write as all x's that are natural numbers such that x's are between 1 and 5 inclusive. So this bar here it is read as such that, and after that you just state the common property of the elements of the set, and sometimes you see this as a colon, or in some texts you can even see this as just a comma. Of course, we have the frequently used sets, the set of natural numbers, the set of integers, set of positive integers. You can also define the set of negative integers, and the set of rational numbers, which is defined here. In fact, the set of the expressions m divided by n, where m and n are integers and n is non-zero. And of course, you can define the set of positive rational numbers in this way. Set of reals, set of positive reals. You can also define negative versions, as I said, and set of complex numbers. And we have the special notation for intervals here. This indicates the set of all real numbers between a and b. And when we have the brackets, it's a closed interval. If you have just parentheses, this is an open interval which excludes the extreme points. And these two are half open intervals. Here in this one, a is included, b is excluded from the interval, and this one, a is excluded and b is included. And the set with no elements is the empty set, denoted either with an empty curly braces or this symbol here. And the concept of cardinality, actually, which we will talk in more detail in the context of infinite sets later on. This is the notation we are going to use for the cardinality of SL. Sometimes you can see S parentheses A is also another notation that you will see in some texts. And simply, this is the number of distinct elements in a set. As I stated earlier, repetitions is unimportant. It's just the number of distinct elements in the set. And based on cardinality, we have the concept of finite sets and infinite sets. Simply, if this set has finite cardinality, we call this a finite set, and infinite otherwise. Okay, so elementary set relations that we are going to talk about are equality and subset. Set equality is defined as two sets having the same elements exactly with no exceptions. Okay, so A equals B can be defined as for all x, x being in A if and only if x is in B. Okay, so when an element is in A, it must also be in B, and when an element is in B, that element must also be in A. If this is satisfied for all elements, then we say A is equal to B. Okay, so set A is said to be a subset of set B if every element of A is also an element of B. So this means there are no elements in A that are not in B. So we can define this as A subset of B is defined as for all x, x being in A implies x being in B. You see, this is similar to the definition of set equality, but we do not have a biconditional here. We just have one implication. X in A implies X in B. In this case, if this is true for all X, we say that A is a subset of B. Okay, if the um, uh, implication goes both ways, then we have equality. Of course, for the notation, we have this symbol, but sometimes you would also see this notation to emphasize a set is always a subset of itself. Okay, and that can be easily shown in this way. And we also have the concept of a proper subset. This is simply a subset that is not the set itself. Okay, simple as that. So A is a proper subset of B is defined as A is a subset of B and A and B are different. Okay, so this is a longer definition, and it involves the subset definition here, and there is at least one element in B in the bigger set that is not in A. So that means A and B are different sets. Now, as I said here, the definitions look alike. And if you have the implication one way, you have the subset relation. If you have it both ways, you have the equality. And here we have that. Okay, if you have A a subset of B and at the same time B a subset of A, then these two sets are equal sets. And here you have a proof based only on the definitions and logical manipulations. Okay, so you just show that this definition is true. Therefore, whenever a set is equal to another set, then they are subsets of each other.